Hello my precious viewers, it's my hope that you are doing great. Welcome to our today's class. It's our third lesson on the topic Hooke's Law. So as usual, let me begin by giving you the quote of the day, which states that before you start thinking that you are too small to make a difference in the world, try sleeping with a mosquito. So we'll discuss that quote at the end of our class today. So today we are looking at various calculations involving the Hooke's Law. And our first example reads that a metal cube suspended freely from the end of a spring causes it to stretch by 5 centimeters. A 500-gram mass suspended from the same spring stretches it by 2 centimeters. If the elastic limit is not exceeded, find the weight of the metal cube. So the first thing to note here is that whenever the elastic limit is not exceeded, then that is a hint that actually the spring obeys the Hooke's Law. So as usual in physics, the first step in performing any calculation is highlighting the key values or the key components that you have been provided by the question. So we are told that a metal cube suspended freely from the end of a spring causes it to stretch by 5 centimeters. I want students to be very keen here. Whenever you are told that a spring is stretched by, then that means this quantity, which is the 5 centimeters, represents our extension. But to some cases, you will find examiners using terms like a spring is stretched from and to. So in that case, you will take the value of to, you subtract from the value of from for you to obtain your spring, the extension. But if you are told that it is stretched by, then that is a clear indicator that this value, which is the 5 centimeters, that is already an extension. So if we look at the metal cube, for the metal cube we are given the extension, which is 5 centimeters. As usual in physics, we convert all quantities in their respective SI unit, and since the SI unit of length is meter, then that means that we have to convert the 5 centimeters into meters. Now we know that 100 centimeters is equals to 1 meter. What about 5 centimeters? So it will be 5 centimeters divided by 100 centimeters times 1 meter, which gives 0.05 meter. Now for the case of the metal cube, we are only given the extension. We are not given the force or even the mass. Now we move on to the other quantity that you have been given. We are told that a 500-gram mass is suspended from the same spring, stretches it by 2 centimeters. Now, if you are told that we are using the same spring, then that should give you a clue that the spring constant for both cases must be exactly the same, because we are using the same spring, which means its stiffness or the spring constant is exactly the same. Now, for the mass, we are told a 500-gram mass. So we are given the mass of that particular quantity, which is 500 grams, so that can help us to find its weight or its force. Remember, the force that stretches the spring is due to the weight of that particular mass. So we know that force is equals to mass times gravity, and the mass you are given as 500 grams, but we know that the SI unit for mass is actually kilogram. So for us to convert the 500 grams into kilogram, we know that 1000 grams is equals to 1 kilogram. So what about the 500 grams? So it will be 500 grams divided by 1000 grams. Then of course we multiply by the value of the gravity for us to obtain our force. So the gravity is usually 10 Newton per kilogram. So you take 500 divided by 1000 times 10, you will obtain 5 Newton. 5 Newton because this is we have converted this one in kilogram, and the gravity is in Newton per kilogram. So the kilogram of the gravity and the kilogram of the mass cancel, so that we remain with units as Newton. Then the other thing you are given about the mass, you are also given its extension. That is, the spring stretches it by. So these are the key terms. By, that simply means that is the extension. So the extension of the mass, that is the mass causes the spring to extend by 2 centimeters. So to convert it into SI units, so 2 centimeters divided by 100 centimeters times 1 meter, you obtain 0.02 meter. So for the case of mass, you are given both the force and the extension. So the aim here is usually to find the spring constant so that it helps you in the other quantity. So the spring constant is also unknown. So remember, from Hooke's law, we already know that force must be equal to Ke. So we are using the Hooke's law because we are told that the spring, provided that the elastic limit is not exceeded, which means the material is obeying the Hooke's law. Now from Hooke's law, we know that force is equals to Ke, where K is the spring constant and E is the extension, whereas F is the force acting. So I'm using the mass, the quantities that have been given for mass, because for the mass I've been given both the force and the extension. So that means that can help me to find the spring constant. But for the case of the metal cube, I'm only given the extension. I don't even have the force. So that means I cannot calculate the spring constant using the values or the dimensions given for the case of the metal cube, because if I try doing that, that will mean I'll have two unknowns. I don't have the force. At the same time, I won't have the spring constant. So that means I only have the extension. So actually, the values of the metal cube cannot help us to find the spring constant. That's why I'm using the values for the mass, because for the mass, I'm given its mass. So that means I can easily find the force. I'm also given the extension. So actually, to find the K is not difficult. So from the Hooke's law, we know that force is equals to Ke. So the force is actually the force due to the mass, that is the weight of the mass, is actually, we have already calculated the weight of the mass as 5 Newton, or the force that is exerting on that particular spring. So the force is of the mass is 5 Newton. Then the extension of the spring as a result of suspending that particular mass, the extension, we have already found it at 0.02 meter. Actually, we are given the extension from the question. We have only expressed it into its SI units. So I have the force, which is 5 Newton, and the extension, which is 0.02 Newton. So if I try to make K, or the spring constant, to be the subject of my formula, then that means I will divide both sides by 0.02. I also divide this side with 0.02. Now the 0.02 divided by 0.02, they will actually cancel out, so that you remain with 1 times K, you obtain K. Then on the other side, I've remained with 5 divided by the 0.02. Remember the 0.02, I've decided to divide it on both sides so that I only remain with K on the other side. So that means K will be equal to 5 divided by the 0.02. So you perform this calculation using your calculator, or by simple arithmetics, you will obtain 250 Newton per meter. So Newton per meter, because the 5 was in Newton, then I'm dividing by the 0.02, which was in meter. So this is Newton divided by meter, which is Newton meter. Now, since the same spring is used, remember our aim here is to find the weight of the metal cube. So the quantities that you are given for the mass have helped us to obtain the spring constant. Now, if we have the spring constant and we are also given the extension due to the metal cube, so if we apply the Hooke's law, we can actually find our force, or the weight. So since the same spring is used, remember, whenever the same spring is used, it means the spring constant is the same, because an identical spring, or exactly the same spring, will have the same amount of stretch. That is, it will have the same amount of stiffness. So that means the spring constant is exactly the same. But you should be keen, because when different springs are used, then the value of K, or the spring constant, can never be the same, unless you are told that the springs have the same spring constant or the same level of stiffness. So we are told that the same spring is used, because they are saying that a 500 is suspended from the same spring, which means the spring constant is the same, and we have already found the spring constant from the dimension of the mass of 500 grams that we are given. So since the spring constant is the same, it means the K for the mass is the same as the K for the metal cube. Now we know that the weight of the metal cube, or the force that it exerts on that spring, according to the Hooke's law, it will be given by Ke. So the Ke, we have said, since the same spring is being used, so the K is the same, which is 250 Newton the 250 Newton per meter times the spring times the extension. Remember, it is now the extension due to the metal cube. So you are told that the metal cube extends the spring by 5 centimeter, which is equivalent to 0.05 meter. So you take K times E, that is the 250 Newton per meter, times the extension due to the metal cube, that is 250 times 0.05, you will actually obtain 12.5 Newton. So Newton again, because the 250 is in Newton per meter, then the extension is in meter. So Newton per meter times meter, this meter will cancel with the meter of the extension, so that we remain with the units being Newton. So actually, the weight of the metal cube is 12.5 Newton. So for part B, we are required to find the length. By what length will the spring stretch if a mass of 1.5 kilogram is attached on its end? So we are given another mass, which is 1.5 kilogram. But because it is the same spring which is used, it means the spring constant is exactly the same. So they want the length. So the first thing is to find, remember from Hooke's law, force is equals to Ke. So for us to find the extension, we need to have the value of force and the value of K. But the K, we have already calculated. The K is 250 Newton per meter, because it is exactly the same spring which is being used. So our only task here is to find the force and then substitute the values in this equation to find our extension. Now, since we are given mass, we know that force is equals to mg, or the weight is equals to mass times the gravitational pull. So the mass we are given as 1.5 kilograms. So you take 1.5 kilogram times gravity. The gravity, we usually take it as 10 Newton per kilogram. So you take 1.5 times 10, you will obtain 15 Newton. So from the Hooke's law, again, we want to find the extension is the unknown. The K is the same, which is 250 Newton per kilogram. So from Hooke's law, we know that force is equals to Ke. So we substitute the force. We have already calculated the force as 15 Newton. That is the force due to the 1.5 kilogram mass. So our force is 15 Newton. That is this 15 Newton is equals to K. We had already calculated K earlier, which was 250 Newton per meter. So 15 is equals to 250 Newton per meter times the extension, which is our unknown. So to find the extension, we make it the subject of the formula by dividing both sides by 250. We also divide this other side by 250. So the extension will actually be equal to 15 divided by 250, which gives you 0.06 meter. So that is how to behave whenever you are given a problem of such a manner. So we look at our next example, which reads that a spiral spring is fitted with a scale pan. The scale pan is at the 40 centimeter mark. So this is the initial reading of the scale that is on the scale. Now when a packet of salt is placed on the pan, the pointer moves to 20 centimeter mark. Now when a 20 gram mass is placed on top of the salt, the pointer indicates 10 centimeters. So part A, we are required to find the extension produced by the packet of salt. So we are told that the spiral spring was fitted with a scale pan, which means the scale pan pointer is at the 40 centimeter mark. So when the spring is fitted with a scale pan, the scale pan causes the pointer to move to the 40 centimeter mark. So this is the initial reading of the scale. But when a packet of salt is placed on the pan, so remember now the weight is due to the pan and the weight of the pan and the weight of the salt. So when we add, the salt is being added on the pan, the pointer moves to 20 centimeter mark. So that means the extension or the spring is stretched by 40 centimeter minus 20 centimeter. So again, be careful with this term. So the initial was 40 centimeter, or where the spring was stretched from, then it was stretched to 20 centimeter. We said if the use it is stretched by, then that means the by is already the extension. But when it is stretched from something to another thing, then the extension will be the difference between those two values. So because the initial was 40 and the final is now 20 centimeter, it means the spring, the salt caused the spring attached or fitted with the scale pan to stretch by 40 centimeter minus 20 centimeter. So the extension produced by the packet of salt will be 40 centimeter minus 20 centimeter, which is 20 centimeter. So to convert into SI units, which is the meter, we obtain 0.2 meter. Then for part B, we are required to determine the extension. What extension is produced by the 20 gram mass? So remember, now when the spring is with 40 is with the scale pan plus the salt, the scale reads 20 centimeter. Now we are being told that when a 20 gram mass is placed on top of the salt, remember the salt is on the pan, and again we are adding another 20 gram mass on the top of the salt. So before we added the salt, our initial reading of the spring is actually 20 centimeter. That is when the spring is fitted with the scale together with a packet of salt. So the scale reading of the pan plus the scale when the spring is fitted with a scale pan and the salt is 20 centimeter. Now we are adding a 20 gram mass on top of the spring with the scale pan and the salt. So it means for this case, that is before we added the 20 centimeter mark, the 20 gram mass, the initial reading of the spring is 20 centimeter. Now when we add a 20 gram mass, the spring pointer indicates 10 centimeter, or it moves to 10 centimeter. So the extension or the spring has been stretched by, that is due to the mass, the 20 gram mass that is added, it means the spring is stretched by 20 centimeter minus 10 centimeter. So the extension is produced by the 20 gram mass. So the 20 gram mass, when it is added, initially the spring is at the 20 centimeter mark. But when you add the 20 gram mass, the spring now moves to 10 centimeter mark. So that means the extension is actually 20 centimeter mark minus 10 centimeter mark, which is 10 centimeters. So remember, we are not taking the 40 centimeter mark minus the 10 centimeter mark as our extension. Why? Because when the 20 gram mass is added, the spring already has a scale pan, is reading already the weight of the scale pan and the weight of the salt. So that means the scale pan and plus the salt, that is the initial reading of the scale when the 20 gram mass is not added. Now when we add the 20 gram mass, the spring stretches from 10 to 20 centimeter. So that the extension, that is for part B, is 20 centimeter minus 10 centimeter, which gives us 10 centimeter. So to convert it into its SI unit, we convert it into meter by dividing by 100, which gives us 0.1 meter. Then for part C, we are required to find the mass of the salt. So remember, the aim in these calculations is always to find the spring constant, because that is the only constant value. That is whenever you are using the same spring, and of course use it with an appropriate value to find the unknown. So our first task here is to find the value of K, or the spring constant. And to find that, from the Hooke's law, we'll look at a quantity where we have been given both the force and the extension, so that we use it to find the K. So if we observe, like for the case of the 20 gram mass, we are given its mass, so that means we can find its weight or the force. We are also given its extension, which is the 0.1 meter. But for the case of maybe the salt alone, for the salt we are only given the extension, but we are not given its mass. So that means if you try to use the quantities for the packet of salt, you will have the extension but no mass, so you cannot find K, because that means you will have two unknown values. But for the 20 gram mass, we can find the force and we are given the extension. So the 20 gram mass is the one that can help us to find the K. So remember, we are using the values for the 20 gram mass because that is what we have been given. We have been given, for the 20 gram mass, we have been given both the force or the mass and the extension. So that's why we are using it to find K. But if we were given the values of the force or the weight of the packet of salt, we will actually use its extension and the packet of salt to find K. But since we are only given the values, all values for the 20 gram mass, so that is what we use to find our K. So if we are given the mass, we can easily obtain the weight. We know that the weight or the force acting is mass times gravity. Remember, for this case, it is the weight which is causing the force or that spring to extend. So force or the weight is given by mg. So the mass is in 20 grams. So to convert it into its SI unit, which is the kilogram, we'll take 20 divided by 1,000, then times 10. The 10 is the gravity. So you perform that calculation, you'll obtain 0.2 Newton. So this is the weight due to the 20 gram mass. Now we have already obtained in part B that the mass causes the extension or the spring to extend by 0.1 meter or the 10 centimeter. So the extension is 0.1 meter. Now from Hooke's law, we can find the K. Force is equals to KE. So the force is the 0.2, then the extension is the 0.1. So if I try to make K subject of the formula, I'll divide both sides by 0.1, which gives me K is equals to 0.2 divided by 0.1, which is equals to 2 Newton per meter. Now the weight of the salt would therefore be equal to KE. So we already have already found K. So if we have K and we also have the force, so actually to find the mass won't be a problem. So we'll use the K, we will use our K and the extension to find the weight of the salt. Because remember, when you get the weight of the salt, weight is equals to mg, so that can help us to find the mass. So weight of the salt, if we use the Hooke's law, that is the weight of the salt is equals to the force produced or the force used by that particular salt to extend the spring. So the weight of the salt will be equal to KE, that is according to the Hooke's law, or the force, which is equals to the K. We have obtained K as 2 Newton per meter. Then the extension due to the salt was actually the weight due to the salt, the weight due to the salt. This was extension is produced by the packet of salt. The extension was 0.2. So the weight due to the packet of salt or the salt will be given by KE. So the K, because it is the same spring used, the K is 2 Newton per meter. Then the extension, that is the extension due to the salt, was 0.2 meter. So you take 2 times 0.2, you'll obtain 0.4 Newton. Now this is the weight that the salt extended the spring by. So that means that is also the weight of the packet of salt or the weight of salt. Now if we have weight, we know that weight is equals to mass times gravity or mg. So if I substitute the weight as 0.4 and gravity of earth we know is 10 Newton per kilogram, then I can easily obtain the mass. So I try to in trying to make mass the subject of the formula, I'll divide both sides by 10. I also divide this other side by 10. So 0.4 divided by 10, you will actually obtain 0.04 kilogram. Someone could be wondering how the kilogram is coming about. So remember here, we are taking the 0.4 is the weight which is in Newton. So we are taking Newton divided by the 10 is the Newton per kilogram, because that is the gravity for Earth, Newton per kilogram. So you take Newton divided by Newton per kilogram. Actually, whenever you divide, you multiply by the reciprocal, so that we'll have Newton times kilogram per Newton. So the Newton and the Newton cancels out, so that we remain with the kilogram. So the weight actually becomes in kilogram. Alternatively, you can also express it in grams, which is remember 1,000 grams is equals to 1 kilogram. So what about 0.04 kilograms? So it will be over 1 kilogram times 1,000 grams, so which gives you 40 grams. But we prefer leaving quantities in their SI unit. Therefore, the mass of the salt is actually 0.04 kilogram. Next, we look at our third example, which reads that a spring extends by 6 centimeter when supporting a mass of 0.06 kg on Earth. when the spring is used to support the same mass on the moon, it extends by 1 centimeter. So you are required to determine the moon's gravitational strength. Then you are given that take the gravitational field strength on Earth as 10 Newton per kilogram. So as usual, the first thing is to obtain the key values that you have been given. So like in this case, you are told that a spring extends by. So this is already the extension. Remember, if we said if you are given from and to, you subtract the two values for you to find the extension. But if you are told that the spring extends by, then this is already the extension. So a spring extends by 6 centimeter when supporting a mass of 0.06 kg on Earth. So on Earth, we are given the extension, which is 6 centimeter. So to convert it into SI units, we divide by 100, which is gives us 0.06 meter. Then we are told on Earth it has a mass of 0.06 kilograms. So to convert that into force, because anyway we will still be required to use the Hooke's law. So the force is mass times gravity. The mass on Earth is 0.06 times gravity, which is 10, so which gives us the 0.6 Newton. Now we know that from Hooke's law, force is equals to Ke. So remember, in these calculations, the aim is always to find the spring constant, then you use it to calculate the other values that are required. So from Hooke's law, force is equals to Ke. So again, I'm using this formula because I'm given both the force and the extension. So that means if I substitute those values, I can easily obtain my spring constant. Then because it is the same spring used, it means if there will be a second case, the spring constant will still be the same. So the force is equals to Ke. So my force is 0.6 Newton. Then the extension is 0.06 meter. So if I try to make K the subject of the formula, that means I'll divide both sides by 0.06. I also divide this other side by 0.06. So the 0.06 and the 0.06 will cancel out, so that I remain with K being equal to 0.6 divided by 0.06. So you perform this calculation either using a calculator or by simple arithmetics or simple cancellation. You'll obtain your K as 10 Newton per meter. So we already have the K. So let's look at the values on the moon. So they are saying that when the spring, so remember they are using the same, they are referring to the same spring, which means the spring constant is actually the same. So when the spring is used to support the same mass on the moon, it extends by 1 centimeter. So the extension now is 1 centimeter. So on the moon we have, they are talking of the same mass. So the same mass as that on the Earth. So remember earlier on we also said that mass is a constant. So whether you take it on the Earth or on the moon, it will still be the same value. So mass is constant everywhere. That is we learned that from, actually I think it was the topic of force. Yeah, that mass is constant everywhere. So the mass is still 0.06 kg. So that means the weight will actually be the weight will not be the same, because the gravitational field strength of the moon and that of the Earth is actually different. So we only know the gravity for the moon, which is 10, but the gravity for the Earth, which is 10. That's why we used it to calculate our force. But the gravity for the moon and that of Earth, they are actually different. So you cannot say that the weight will be equal to mg and use g as 10. No. If it was Earth, then that will be okay. But because the gravity for Earth and the moon is different, then you cannot use 10 as the value of gravity for the moon. And in fact, that's why we are asked to find the gravitational field strength for the moon. So we have the mass for the moon, and we also have the extension on the moon. The extension on the moon is, we are told the spring is stretched or extended by 1 centimeter. So in its SI unit, it will be 1 centimeter divided by 100, which gives us 0.01 meter. So since the same spring is used, it means the spring constant, that is K on Earth, is the same as the spring constant on the moon. Why? Because you are using exactly the same spring. So the spring constant is 10, because we had already calculated it here as 10 Newton per meter. So from Hooke's law, we know that force is equals to Ke. So remember, if we want to find the gravitational field strength on the moon, then we at least must have the force and the mass. We are given the mass, we are now looking for the force, and we are using the Hooke's law to find our force. So the force is given by Ke. So the K, of course, is constant, which is 10 Newton per meter. Then the extension on the moon was 1 centimeter. So in meters, we have found that it is 0.01 meter. So you take 10 times 0.01 meter, you'll obtain 0.1 Newton. So since we already have the force, and we know that the force is actually the force that is stretching the spring is produced by the weight. So the force is equal to the weight in this case. And we know that the weight is given by mass times the gravitational field strength. So the weight or the force on the earth is 0.1 Newton. Then the mass on the weight on the moon is 0.1 Newton. And the mass on the moon, we are given the mass on the moon as 0.06 kilogram. So that means if we substitute those values in this equation, it should be in a position to give us our gravitational field strength for the moon. So the weight is 0.1, the mass is 0.6 kilogram, and the gravity for the moon is our unknown. So if I try to find G, then that means I will make G the subject of the formula by dividing both sides by 0.06 kilogram. So I'll divide both sides by 0.6 kilogram. So the 0.06 kilogram on the right hand side cancels out, so that we remain with G being equal to 0.1 divided by 0.06. So you perform this computation, you will actually obtain one whole number 2/3 Newton per kilogram, which is approximately 1.667 Newton per kilogram. And if you refer from our topic of force, whereby we were calculating the weight, we actually did say that the value of the gravitational field strength on the moon is actually approximately this value, that is 1.66 Newton per kilogram. You can refer to our previous clips on the force, whereby we are talking about the weight and the mass, and you will realize that we actually said that this is the value for the gravitational field strength for the moon. So having performed those a few examples, I expect that you are now in a position to handle a few exercises here. So at your own free time, try this exercise. So the first one is that an object of weight 20 Newton attached at the end of the spring causes an extension of 0.5 centimeter on the spring. So A, you are required to determine the spring constant of the spring. So I've performed the calculation, and I expect you to find this value or this answer. Then determine the weight of the object that will cause an extension of 0.86 centimeter when attached to the end of the spring. So again, I've performed the calculation, and I expect you to find this. Then the last exercise reads that a light spring, a light spiral spring which obeys Hooke's law has a length of 6 centimeter. Its length increases to 8.5 centimeter when supporting a 5-gram mass. So you are required to determine the mass of the stone if the length of the spring becomes 7.5 centimeter when supporting the stone. So again, I've also performed the calculation, and I expect you to find 0.003 kilograms. So actually try this exercise. They will help you to reinforce those concepts that we have handled. And in case you have any challenge in handling these exercises or any understanding any of the examples, feel free to drop a comment in the comment section of this video, and of course I'm there to respond. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day stated that before you start thinking that you are too small to make a difference in the world, try sleeping with a mosquito. So what does this quote mean? So we all know what serious health issues a mosquito can cause us, regardless of its tiny size. Yeah. For example, a mosquito can actually cause you malaria. So there are those of us who tend to think that they are still too small to make a positive difference in the world. My friend, that is not just true. I'm here to fight that belief and to challenge you to make a positive difference in someone's life using your own small means. For example, just by helping a blind person to cross a busy road or encouraging a depressed person, that is already making a positive difference in the world. We tend to think that you have to do a great thing for you to make a positive difference, but sometimes just helping someone or sharing an idea can be the idea that that person needed actually to make a difference in their life. So actually I challenge you to do small acts of kindness that can make a positive difference in the world. And remember that you don't need to be great for you to do great things, but you need to do great things, to do small things in a great way for you to be great. And lastly, do small things with a big heart. Thank you. Until next time. For those who have not subscribed, kindly do so. It really does help me to grow the channel. And in case you have your colleagues, that is some of the students or anyone that you know that these materials or these lessons could help, kindly do me an act of kindness and share this channel to your colleagues or to anyone that you think this content will be really helpful to them. If you have enjoyed the video, feel free again to like, comment, or even subscribe, and also turn on the notification bell so that whenever I upload a new video, you will be the first person to get a notification. Thank you. Until next time.